Okay, so for the makeup, I can show you what happened. So if you did a good job in your first exam, you have no idea what happened to the makeup. But I think I built a system which is even closer to real situation when you are applying optimization. And I hope everyone understand this kind of process. So in the future, you know how to implement optimization in real world problems. So the problem was, let me go to the, where did I? Okay. The problem was this. It's looking very similar, but here I said you're going to minimize the problem using Newton's method with finite difference. The only way for you to do derivative is to do finite difference. Otherwise, you have no idea what to do. And this time I ask everyone to start from 0, 0, 0, so you don't make a random guess that may not be good for the optimization process. I set up the termination criteria, and I said, I didn't mention anything about the function. The function, we call this kind of problem is like a black box. You don't see what's inside. It's just a system. But you can put numbers into the system, it will give some value back. In reality, in the world, it's always like that. You have your design variables, and then you implement it to some kind of system, it will give you some result. For most of the time, it's very difficult for you to truly formulate a function that properly describe the function itself and its relationship with the variables. Sometimes it's very difficult to have something like that. For example, if I'm a clothes designer, if I'm looking for some kind of performance comfort level, and I have design variables of maybe the thickness of the wire for the clothing, and maybe another variable would be the size of the bottom, something like that. I can have multiple variables defining the cloth. But how are they related to the comfort level, comfortness? There's no function that describes the comfortness, comfort with respect to the variables I mentioned. But what you can do is, you can try a combination of the variables in real life, and then truly make the clothes. Ask 10 people to wear the clothes, and give you a score. Maybe take an average. Okay, that's the score for that kind of clothes. Then change the parameter a little bit. Do the same thing again, you will get another function value of the comfort level. So at the end, if you truly apply optimization in that kind of process, you will be varying your variable with a certain way, and you will get a bunch of responses, and then you need to make a decision what will be your final design. What people usually do is to sample the variable. Let's say you have let's say you have a real problem. And for many designers, they may have, okay, 3 variables, and they are looking for the responses. So what they may do is they will define so-called define levels. So maybe there's a low level, middle level, and a high level. They can choose 3 levels for each value. Let's take, just give random numbers as examples. Maybe 3 levels for x1 is 1, 2, and 3. For x2 probably is something else. It could be 0, 10, and 20. And maybe x3 is something smaller, 0.1, 0.5, 0.9. Okay? So basically you have 3 choices for each variable. So the combination would be 3 to the power of, to the third. So you have 27 combinations. So what people usually do is to truly evaluate the function with those 27 combinations, and there must be one good solution out of the 27. That's what people usually do. They just pick up the best one from those 27. But they cannot guarantee that's optimal. But in many research work or thesis, they said that's the optimization process they did, that's the ultimate. They use the word ultimate. But in fact, they can only say that's the best result out of their selection. Okay, so in this course, we hope to teach you something so that initially you have a guess. So when k equals to 0, you guess. For example, you decided you choose to do this. Okay, and then you are going to figure out a way to compute the derivatives. So you are going to try different positions of the variables. And with finite difference, you should be able to evaluate the gradient, or if you want to use Newton's method, you can evaluate the Hessian. And there's an equation for you to find the minimum point out of some assumptions. And supposedly, you can find the optimal based on this systematic procedure. And there won't be any point out of the 27 combination. That would be somewhere you have never tried before. Like in the makeup exam, you have no idea where the solution is. Now I'm going to reveal how I built the problem. So over here, I created this form. So in the form, you need to specify who you are. Take myself as an example, I choose myself. And you are going to give me some x1, x2, and x3. So just as an example, I can say 10, 10, and 10. Okay, I submit. Then how do I evaluate the function value? There's a response Google Sheet right here. The hyperlink can be found right here, the Google Sheet. So go to the Google Sheet. Go to the tab under your name. Then 10, 10, 10 was the trial. So this sheet will give me a response of the function. But it doesn't show any hint about the function itself. You have no idea what happened. So I'm gonna let you know how I did it. So inside, even you come to this series of responses, you you don't see anything. But if you look at this one, there's a function called import range. So I hid the function in an additional file with no access to any others. So even you use this to go to the other file, you shouldn't have the access to take a look. So in the other file, I'll call this magic function. This is the file where I compute everything. So over here, it was an import. So I imported what you sent to the Google form, and this part, whatever you sent, was imported to this magic function. Over here, I set up certain equations, and at the end, it's a polynomial. It's a polynomial, and the true solutions are here. These are the true solutions. Actually, in sheet 2, these are the true solutions. So it's a polynomial, basically coefficients, and x1 minus 2.52, x2 minus 4.8, x3 minus 5.5. So everyone has a different solution, okay? And it was randomly made, so everyone should experience differently. So take myself as an example. The true solution of my random function is these, okay? So if I try these as an input, of course only I know, right? But if I truly try those as an input, let's see what would be the response. I actually want more digits. Let me put in the real solution into the Google form. If I do this and submit, and go back to here, you will see the input I just made after several seconds. How many? You try? How many? Ooh. Okay. Okay. So from here, if I throw in the real solution, the response is 0. So yesterday, if you got a 0 right there, you found the solution. But it's almost impossible for you to find this many digits at the end. So if you use Newton's method, for example, probably what you get at the end are only having an accuracy of 3 digits. So let's say you submit a solution that has 3 digits of accuracy, and let's see what the answer would be. So 3 digits. And then -4. So if you submitted a solution with only 3 digits of accuracy, you will get something really close to 0, but not 0. Very close to 0, right? So if yesterday you found something that is very close to 0, you did it right. Let me see. Okay. So this guy probably did a good job. You found something close to 0. So if you didn't experience anything close to 0, you did something wrong yesterday. Okay, I quickly checked some of your some of your PDF, some of you still didn't figure out what happened. Okay, so I hope later on, don't give up on yourself. Still go back to see how to find the true solution. Okay, so I made a video yesterday. The video already introduced how you can do finite difference. I guess you guys, some of you didn't really understand how to do finite difference. So please go back to the notes. Okay, I know it's very troublesome, but in real life, that's the only way you can estimate the derivatives. Because in real life, there's no true function. How do you take derivatives? You can only estimate it. And the only method that teach you how to do estimation of derivatives is finite difference. Okay, so everyone should know how to do it. Okay? I remember some of you did a pretty good job. Let me see. Maybe, okay. So this person started from 0, 0, 0. He increased delta x on x1, x2, and x3. Then he decreased delta on x1, x2, x3. So he's doing exactly what I'm looking for, because he tried to compute the Hessian. So not only you need to have increment on x, you also need decrement. And you need increment on 2 out of 3 once in the time. So increment on x1, x2, increment on x1, x3, increment on x2, x3. If you have no idea why he did this, that means you have no idea, you didn't fully understand finite difference. When you see this, if you think, okay, this is right, then you understand finite difference. But I think this part is not necessary. So for this person, Dawanga, I don't think that those are not necessary. These are not necessary. Because for finite difference, you only need to have one step further and one step backward, and also the off-diagonal step. Basically, these are enough. So if every trial costs you $10 US, you owe me some money already, right? In real life, it's like that. So when you do your own experiment, you are going to tell your professor, hey, I'm gonna try this several times. And if he allows you to do it, he basically invests in you. But if you try your experiments at some design positions that is not necessary, you're wasting his money, right? But professors won't be that bad and then come to you and say, hey, pay me back. But you need to learn how to do experiments more effectively. So we don't really need increments like these. So I don't think these are necessary. Maybe Dewanga try a different way to do finite difference. I don't know. I need to go back and check. So I guess after the 19th trial, he performed one iteration and then advanced to the second iteration. So I guess this was his result based on the Newton's method in the first iteration. So he started to use the same trick. He started to have increments. But this part he didn't do it right. If this is the initial point of your second iteration, when you apply small increment, you apply on top of this. You will never try this again. You will not try something like this. You basically add a small value on x1, but keeping the same on the x2 and x3. So he should be trying a lot, many of those multiple times, but every time have small increment on the right spot. So he should try something like this. He should apply all these on top of this point and do exact same thing again and continue to do this until it converges. Okay? Okay, so maybe I'm not sure if he had small increment. Okay, yeah, he has small changes on the digit, yeah. But you can tell the change is very small. There's a slight change. Okay, anyway. So I think from here he's doing the second problem. So I think he failed the first problem because at the end the function value is super large. For the steepest descent, did he get, somehow he was able to find a point like this? It's really close to the true solution. Okay, let me see who else did a good job. No? No? Let me see who did a good job. Oh, okay. Maybe Junxiang did a good job. Zhexuan. Oh! He was able to find this point. So maybe he did it right. Maybe. Taijun didn't do it. So if you did it right, you're supposed, at least you didn't do it. You're supposed to find somewhere close to 0 because everyone's optimal is 0. Okay. Yeah. So like phone, you were able to find something. So like this one is completely not necessary. You don't even need to just test the system by 1,000. I should charge this, then you will make those moves in a more effective way, right? Okay, anyway, so that was the mega exam. If you still cannot understand what I was looking for, go back to the notes, go watch my video again. If you still cannot understand, you can come to me. I will teach you. Okay. For Taiwanese, I will teach you in Chinese after the class. Maybe it's the language issue, or I don't know. We already tried this multiple times. I even write computer codes. If you follow the code, you should be able to figure it out, right? So I cannot figure out a better way to teach this. I really hope everyone understand how to do this. Okay, so that's the comment I want to give on the yesterday's mega exam. And last time we did linear programming. So how was it? How's the homework? Did you find the solution? Okay, so it should be a problem that is doable. Do you enjoy linear programming more or gradient-based approach? None of them. No one enjoys. Today I'm going to show you how to program linear programming in MATLAB. Okay? Based on the course schedule, are we almost reaching the time for the next exam? So based on the course schedule, so today I think I collected the linear programming homework and the conjugate gradient completed. So this weekend, I'm supposed to give you an exam. We haven't covered the conjugate gradient part and linear programming part. I will give you two problems. First one you will solve by conjugate gradient, second one solved by linear programming. Okay? They shouldn't be long, because for conjugate gradient, the gradient direction will be updated effectively, so you should be able to converge at the right position. And for linear programming, I should give you a problem that is solvable, just like your homework. So you should be able to find a solution that with a converging process. Okay. So when you do the exam, if you cannot converge properly for both problems, something is wrong. Either is my problem is wrong or your process was wrong. And if you realize, if you're doing conjugate gradient and if I ask you to do finite difference again, then your estimation of the gradient has to be accurate enough. Otherwise, it could diverge. So it really depends on whether I would like to do finite difference again. If I don't, if I just give you a function and then you can directly take derivatives, then it's easier for you because it's an accurate calculation of derivatives. So conjugate gradient should be able to find a solution more effectively. So it really depends on what kind of problem I would like to give you. Okay, depends on my mood. On Friday night, I usually give away the problem on Friday night. Okay, so today I will show you MATLAB coding for linear programming. And later on, during my coding, I will need to use some of the equations that I introduced last time. So I want to remind you what are the equations I use. Once I switch to the screen of my laptop, then it's difficult for me to switch back and forth. So I will let you know what I will be using, and then later on you only see MATLAB coding. So later on, to make my life easier, I will just give myself a problem that has equality constraint only. So I'm not going to do coding for inequality constraint, converting to equality ones with slack variables. It's doable, but I don't really need to program that part for you. So you won't see this. You won't see slack variables or surplus variables in my coding. Later on, you won't see the derivations. You will just see how we did in the solution process. So in my coding, I will be formulating the problem just like this. Several matrices. A vector of C, a matrix of A, and a vector of B. I need those numbers. Okay? And then I will have a decision vector to decide which one is basic, which one is non-basic. And then every iteration I will be computing for the, which one? The black one, the bit black one. I will do the transpose thing. And then I will be finding which coefficient is the most negative. And then I will be computing for A hat and B hat and do the ratio test. And in the ratio test, I will be choosing the smallest positive one. After that, I will be swapping the the decision of basic and non-basic on top of the two chosen variables. After the swapping, I do another iteration until I will not see any negative values for this check. Then I will convert. So I will do this for you to show you. Okay? And if possible, I will do some plotting for the iteration process, so you will see how the design point is truly moving toward the boundary, like I said. Okay? So let's do this. Next week we will be talking about something called quadratic programming, and then I will show you how to use a MATLAB function called fmincon. After fmincon, your life will become easier because we will be using fmincon, and you don't need to do the math by yourself anymore. And you will realize how thankful you are. How thankful you is fmincon. You will be so happy that MATLAB already have this fmincon. Okay. Anyway, let's go to the create a new script. So I'm gonna call this file LP. So initially I need a C vector. So I will just solve the homework. Solve the homework. So for the homework, -6, -1. I don't want to solve the homework because I need to convert. So I will just solve the example that I showed last time. So C is -1, -2, 0, 0, 0. And then the A matrix is, let me just use capitalized. Capitalized, -2, 1, 1, 0, 0. -1, 2, 0, 1, 0, 1 and 0, 0, 1. B vector would be 2, 7, and 3. So this was the problem that we were solving. Yeah. So you start with a decision of the basic variables. So I'm gonna call a variable basic, and and the zeros are representing which column is num. 1 is representing which column is basic. 0 is representing which column is not basic. Okay. So this basic variable in MATLAB would be how I decide which column is basic or non-basic. So later on, I need a general code for me to determine what is Cn, what is Cb, what is An, Ab, and so on. So let me write the code. Cn actually would be so So the basic ID would be basic dot product. So dot product multiplying 1 to 5 vector but transpose. So you will have 0, 0, and 3, 4, 5. 0, 0, 3, 4, 5, and they want to get rid of the 0. So I will say, how do I get rid of 0? Set difference. 1, 2, 5. Let me just check. Set difference. 1 to 5 and 3 to 5. Set difference tells you what? Let's see. Can I do this unique? Okay. If I use unique, then kill the first one. Okay. If I use unique, after unique, and then I will sort. Okay, try this. If I have 0, 0, 2, 3, and 4, after that, I will have 0, 2, and 3, and 4. Yeah. So I just need to delete the first one. So basic ID first one equals to empty. Okay. So what happened? I have a basic vector. It's a horizontal vector 0, 0, 1, 1, 1, or it could be 5 numbers. 3 of them will be 1, 2 of them will be 0. And if I do a dot product with 1 to 5, when one of the basic is 0, at the end, the 1 to 5, that particular one, the corresponding one to the 0, will become 0, right? So basically, I'm doing a dot product like this: 0, 0, 1, 1, 1 times 1, 2, 3, 4, 4, and 5. I'm doing a dot product like this. So that's why on the right-hand side, I need to do a transpose, because horizontal times vertical. So at the end, you will, no. I shouldn't do dot product. I should use so-called element calculation. So not dot product. I should do this. So in MATLAB, there is a kind of multiplication. It's called a point multiply. So when you do point multiply, it's a element calculation. So the first element will be doing whatever operation you have to the first element on the right on the second term. Second element will be doing the same calculation to the second ID on the right. So it's gonna be a 0 times 1, 0 times 2, 1 times 3, 1 times 4, 1 times 5. So at the end, it's still a vector. So it's a very unique calculation in MATLAB, the point multiply. So if I do point multiply, then I don't need to do this. So let's try it. At the end, the basic IDs. Oh, something's wrong. Let me debug. Okay, so from here, if I use basic, multiply this. No. What? Base. Maybe I do this. Okay, so I need a bracket. So after you do that, if you say unique means in a vector, if you have duplicated content, only the unique one will be selected. So I have 0, 0, 3, 4, 5. After unique, only 1, 0 at the end. So I just need to, I need to sort it. Because if one day I have, for example, the first one is 0, first one is 1, and the fourth one is 0, I will have a vector like this. So I want to sort it so the 0 moves to the first one. So if I sort, if I say unique, unique sort, unique already sort, but just in case I will sort it by myself. So I have a unique and sort. So I'm pretty sure the 0 is the first one. Then I claim the first one will become empty. So the first index of the basic ID will be disappeared. So let me repeat that again. At the end, basic ID becomes 3, 4, and 5. So in computer, I finally get what are the IDs for the basic columns. The third, fourth, and fifth columns are the basic ones. And I will need the non-basic ones. So I need a non-basic ID. And there's a function called set difference. And here I can say 1 to 5. And the second input will be the basic ID. If I do that, non-basic ID will be 1 and 2. See, basic ID, 3, 4, 5. Non-basic ID, 1 and 2. So once I have the IDs, I can make good use of those. And even I change the beginning. If I say, like I said, the order of the basic is not 0, 0, 1, 1, 1. Even like this, once I complete the code, the basic IDs will be 1, 3, 4. The non-basic will be 2 and 5. So with these lines, I get the IDs for the columns. Okay, for the basic columns and non-basic columns. Okay, so that's really helpful for me. And I need to do this every time at the beginning of the iteration. Later on, I will need to get what is Cn and Cb. So Cn will be basically C and 1 comma and non-basic ID. Okay. So now you realize why do I get the index for the basic and non-basic, because I can do this so effectively later on. So now you can see my Cn. Cn can be obtained so effectively. Okay, if I get the ID first. So my CB would be same code, but here basic ID. How about the AN? Basically A matrix, and all of them in the first one, second one, non-basic. So A basic, here basic ID. B vector is always the same. So you will need to compute all these. So let's run the code once again and see if I'm right. So CN, -1, -2. CB, 0, 0, 0. AN, just like what we did in the first example. And then AB. So effectively, we get all the equations, all the matrices that we need. So the next will be checking CN minus CB times AB inverse times AN. So this, I'm gonna call this coefficient, because this is a coefficient for the coefficient for the basic variables, the non-basic variables, and we are looking for the most negative ones. So once you compute this, your coefficient will be just like what we did, -1 and -2. And then we're going to pick up the most negative ones. So we need to know what's the ID for it. How do we pick up? We will probably have a for loop from the first one to the length of coefficient. And then we will have a actually, we don't need to do this. We just need to find the minimum. So minimum coefficient, and then for the output, so basically this is the mean coefficient, and then mean ID. Okay? So what this code did was, you can find what is the minimum value inside this vector, and the output is that minimum vector, and also it tells you which index has the minimum value. So if we do that, what at the end, mean coefficient will be -2, and the mean ID is the second one. But later on, when we are almost converging, the mean coefficient may be positive. So we only continue if the mean coefficient is negative. So here we need to stop if the mean coefficient is positive. So we can program that later on, because I want to have all the required codes done, and then work on the iteration, work on the loop. So this check is necessary when we have the code for the loop. Okay? So we can do that later. Now, when it says the mean ID, actually is the index for the non-basic. So right here, our mean ID is 2. That means the second one in our non-basic variables. So in fact, the one to be swapped would be second index in the non-basic ID. So the second index inside non-basic ID would be the index that to be swapped. So I will say, so the ID from non-basic to basic equals to, here is the collection of our current non-basic ID. So the first one and the second. So it's the second one out of this vector. So here, in ID. So the ID that will have was originally non-basic, it will be converted to basic later on. So using this code, I know, okay, that this particular ID will be swapped to basic later on, right? So this is the first half of the loop. We now need to move on to the next half. We need to do the ratio test. So for the ratio test, we need to compute A hat and B hat. So let's do A hat. For A hat, you're going to do AB inverse times AN, and the B hat will be AB inverse times B. But for the A hat, we are going to choose so-called the J column in our notes. What is J? J is gonna be the mean ID. So so-called the A hat and J column will be A hat and choose the mean ID. Okay? Because from our note, we have two coefficients, both negative, -1 and -2. If you check right here, the coefficient was -1 and -2. So the second one was chosen. And for the A hat, it was a matrix. Only the second column will be used. So right here, this gives me the second column. Let's run the code and check what they are. Over here, let me run the code again from the debug mode. So basic ID was 0, 3, 4, and 5 due to that dot multiply. And then I eliminate the first one because there's always a 0. So after eliminating the first one, then I realized the basic ID is 3, 4, and 5. So non-basic will be using the set difference. I get it's 1 and 2. So CN, CB, AN, AB, I can compute effectively using those IDs. CN, CB, AN, AB. The coefficient based on the node, we need to do this. So after the calculation, I got -1 and -2. Use this mean coefficient at the end. The minimum one is -2, and the ID is the second. So the second one has the smallest, the most negative ones. And I will do this check later on. If the minimum one is positive, I stop. So the non-basic ID is 1 and 2, and the second one has the most negative one. So the second one from 1 and 2 is 2. So if I do this, the ID to be converted from non-basic to basic will be the second column inside A matrix. Second variable, x2 basically. Okay, A hat, compute A hat and B hat. A hat is a matrix, B hat is a vector. And for the A hat, we only need the J column. J is basically mean ID, the second component that we found from this coefficient check. So that's why I said A hat and then second column. If I do that, A hat J will be 1, 2, and 0, just like the node. Okay? Now we can do the ratio test. And when we do ratio test, we need to be careful because we don't want to divide it by 0. So I'm gonna do a for loop, and from the first one to the last one, so length of B hat, okay? If B hat of the index is 0, we do nothing. We don't care about that one because that one has the ratio test of infinity, and that will we don't need that one. So we can do not 0. We only do ratio test when it's not 0. So let me see. This is this. Yeah. So this and equal sign, this is not 0. Only if the we are doing A hat over B hat. So actually here should be A hat and the Jth one. Okay. Because it's the ratio test is B divided by A, right? So we don't want the bottom to be 0. So if it's not 0, we compute it. If it's 0, we don't even care. So then we will do B over A. So the ratio and the index equals to, how about this? If it equals to 0, we will assign a large number, very large. So that one won't be chosen. Is that? No, I don't think we should do this. Let me think about a good way. Or just make it infinity, because it is supposed to be infinity. Is that good? Let me see. If I say 1, infinity, 2. Oh, yeah. Okay, so MATLAB can handle infinity. So how about this? Okay. So if MATLAB can handle infinity, then it's fine. We don't even need to do this check. Just compute the ratio. So the ratio is B hat divided by A hat J column. So if it's infinity at the end, that particular one will be infinity. And then we're going to choose the smallest positive one. This part is tricky because we don't want the negative one. It's possible we have negative here. So if we have negative value, what do? We will, I don't want to use a for loop. Do we use a for loop? For the negative value, okay, if there's a negative value, we will convert it to a positive infinity. Okay, then how do we do it? You still have a for loop. Okay, and then if ratio, the ith one, smaller than 0, that means it's negative. Then I will convert it to infinity. Okay, why do I do that? Because I would like to use the same trick. I will use the mean function. So over here, again, here, mean ratio. And I'm gonna call this mean ID2. And mean ratio. Okay? So if it's negative, it will be thrown to the infinity. So when I do the mean ratio, I won't be able to pick up that one. Only the smallest positive one will be chosen by this line. Once I have it, I know the ID for basic to non-basic will be the basic ID and then mean ID2 here. Same trick. Okay, let's take a look if it works. So let's do the debug mode up to here. So when I do the ratio test, the ratio is, no. Oh, I should use dot ratio, the point ratio. Otherwise, it's a vector divided by the vector. So do it again, repeat it again. P hat a vector, A hat J a vector, vector divided by a vector, you need to use point operation. So the ratio test gives me 2, 3.5, and infinity, just like what we did in the note. And then there's no negative values, so we don't see this. But let me just intentionally convert the first one to negative. For example, if one day -1, the ratio 1 is a negative value. Then in this loop, ratio 1 will become infinity if there's a negative value from this code here. Okay, so let's run again. In this case, we don't have a ratio that is negative, so this for loop won't be active. It doesn't matter. So none of them will become infinity due to this negative check. So let's keep on doing this until it reaches here. So ratio is remaining the same. And here the mean ratio would be 2. So mean ratio is 2. The mean ID is the first one. So the first one has to be swapped. So the first one inside basic ID. Basic ID is 3, 4, and 5. So the first one out of 3, 4, and 5 is 3. So from here, the ID to be swapped from basic to non-basic is X3. With this code, I found ID 2, X2, to be swapped from non-basic to basic. ID 3, X3, to be swapped from basic to non-basic. Okay, so that's a complete process. Okay, so I need to do this repeatedly until everything converges. So I'm gonna do a while loop.
Professor,
yeah.
How if the ratio is 0? Because 0 is not positive, right? Is the input the smallest positive?
You mean this check?
Yeah, I mean.
Because I don't like negative values.
Yeah.
When I do minimum ratio,
is 0 input to smallest positive? Because what I know 0 is not positive.
Let me think. If it's 0, then if it's 0, that means the function is very straight. Okay, we cannot choose the 0 one as well. So in that case, put the equal sign here. If it's 0, we throw it to infinity. So why is that? Let me show you in the note. I didn't cover this part last time. In the ratio test, we draw this line, right? So in the case where we have the ratio test equal to 0, that means a function is like this. It goes to 0. So there is a linear function that regulates the x2 and that particular corresponding variable, and it only allows this linear relationship. So it doesn't allow x2 to be increasing. In that case, that corresponding variable is not the one we want to choose. And if that happens, maybe this problem is not solvable. Yeah?
What happens if all values are negative on the ratio test?
Say again?
On the ratio test, if you find all values are negative, is that mean convergent or not?
Oh, in the ratio test, if they are all negative,
Yeah.
then you are in trouble. Yeah.
So in the homework I found...
You found negative? Really? So maybe my problem is not solvable.
对。
We'll see. We'll check later on. If my problem is not solvable, that means I'll give you full mark. But it's just homework. We will check later on. We'll see. Okay, so you're supposed to choose the smallest positive. Anyway, we'll see. So. Let me have a converge check. If it's not converged, then we need to keep on doing this. So when do we say it's converged? When the minimum coefficient is positive. So here, if mean coefficient is positive, how about 0? Maybe also 0. Then we converge. Converge equals to 1. So this line, if the minimum coefficient is positive or 0, that means we cannot find the most negative coefficient. That means your objective function cannot be improved. Then we will change this value to 1. Then when this is complete, when you go up to here, it will just stop. Or we can just say break. Let me see. While 1 break. Okay, so break ends the while loop. So we can just say while 1. Okay. While 1 means repeat this. While true, do this. So only the break breaks the whole loop. Okay, let's see. I forget to swap. Okay. At the end, I need to swap the digits. Otherwise, it will just keep on doing the same thing. So basic, the ID of non-basic to basic will become 1, and then the basic to non-basic will become 0. Yeah, you need to do that at the end. Okay. Okay, finished. So I didn't have. I want to print out the result. So maybe I will show something like an iteration number. So here, iter equals to iter plus 1, just for me to show the result. So at the beginning, I will say linear programming starts, and your design variable is basically you need to compute for what's the current variable. So the current variable, if you want to compute it, it's actually right here. If you want to compute for your variables, basically A basic inverse times B. That's your variable, right? So, maybe I do it here. Once you, okay. Let me do it here. So X, the basic IDs equals to 0. And X, non-basic IDs equals to 0. And the basic IDs equals to A, B inverse times B. So here I did X non-basic equals to 0. X basic will be A, B inverse times B. I need to do this after I have the A, B right here. Let me just check if it's right. Okay, so my X, yeah, 0, 0, 2, 7, 8. Okay, so every time I will be able to compute my X. Let me add an iteration number here. So iter. They are horizontal. So I should do this. Comma iter. Okay, so let's do it again. So for the after, they become vertical. Do I want vertical? I think I will have horizontal. Yeah. I should use. Do I want vertical or horizontal? It doesn't matter. It is supposed to be vertical. Yeah, so this is okay. Or maybe if I do this, yeah, horizontal is fine. So later on, if I continue the second iteration, that will be my solution. Second iteration. Okay, so yeah, I was able to compute everything. And let me run the code again to finish the whole thing and see the X. So that's the iteration process. So we care about the first two variables. This is the original variable. We started from 0, and then we went to 0, 2, and then 1, 4, and then 3, 5, and converge. Let's plot out the function and then observe what happened. If you want to plot the function, you need to say figure, and then easy contour, And oh, I may use symbolics. X1 and X2. Here I will have C1 times X1 plus C2 times X2. And I will be plotting from 0 to 10, 0 to 10. Let's see. Wait. What? Y44. C1, C. Yeah, why not? Okay, so it was running its drawing module. Okay, I want this to be axis equal. Hold on. Set GCF color white. Set GCA font size 10. Yeah, let's see. Oh, 10 is too small. Okay. Title, nothing. We don't need this. X label, X1. Y label, X2. Okay, let's do this. Oh, not X label, label. So you have something like this. And now we need to draw the constraints. So the constraints, they are linear functions, so easy plot. And y equals to, so it's gonna be, and you need a for loop to the size of A1, and then for each one, easy plot, and then so I'm gonna do, for easy plot, I need to do this. Because it's a function like A1x plus A2x equals to B, something like this. Can we smaller than, right? So for easy plot, what I can do is I can do this. And then I divide everything by A2. So you're plotting this function. Because easy plot has to be you only have one variable, so y equals to ax plus b. So you tell the MATLAB the right hand side, and you will draw a straight line over there. Okay? So draw the negative I1 divided by I2 times, here you can say x1, plus the I1 divided by I2 plotting zone 0 and 10. Say H, and then set, oh, you can say HI, a handle for the plot, and then set H line width to color black. Easy plot. Run the code. So, why is that? The third function is a straight line. Yes. The third function cannot be drawn easily because it's a straight line. The straight line, how do you draw the straight line? So what happens when it's a straight line? When the AI2 is not 0, then you can draw a straight line in that. But if AI2 is 0, then you are dividing by 0. That's why it's a straight line. So in that case, you are drawing a straight line. So HI, you can only use plot. So where is that position? It's basically B divided by A1, then 0. Yeah. And draw this to 10. Okay. That should do it. Not what I think. Sorry. It should be like this. Two x1, the first x1 and the second x1, first y1, first x2 and second x2. Then you have a straight line. Okay. So the problem was like this. Something is wrong. Something is wrong. Did I draw this properly? It shouldn't be like this. What was the problem? Okay. I know why. He was right. I need to, once it's done, I need to change the space again. Where was my plot? Here. Y limit goes from 0 to 10. Okay. There you go. So this is the design space, okay? And I'm gonna plot out, I'm gonna say title empty. And I'm gonna, whenever there's a solution, I'm gonna draw a dot over there. So whenever I have this X space, when I have done with this, I can plot the iteration and the first one, and then X iteration, second one. Draw a red circle, marker size 10. Okay. Not large enough, 30. Then you realize it's surely trying to move along the linear boundary and then reach to the top. Okay, just like what I showed you last time in the iPad. See, it's moving this way. Now let's check the homework. Let me get one of yours and then copy the first equation. Okay. Let me try this. Okay. I'm gonna hide this one, and then for the problem, if this person is doing this right, -1, -2, 1, 0, 0, 1, -5, 0, 1, 0, 7, -1, 0, 0. Okay. Maybe he's right. Maybe, I don't know. -6. No, he's wrong. B has to be positive. He did it wrong. Okay, let's try this person. So that person definitely did the homework wrong. Okay, -1 here each. Okay. Okay, it looks right. 6, 4, and 40. Okay, let's see. Oh, okay, no, hold on. Maybe something's wrong. It doesn't converge. Okay, let me know. Say again.
The 2 should be positive. A 的2对1 2
yeah. -1, +2. That's what he wrote. Okay, let's try it again. Okay. Something's wrong. Yeah. Okay. It looks alright, but somehow. Let's check iteration by iteration. Okay. So this was a problem. And okay, that's the starting point. Good. Okay, now here. Let's see. Okay. Something went wrong. Why? Something went wrong this time. So the basic vector, where's the basic? Basic is it not solvable? Let me formulate by myself, just in case. Okay. It looks right, but I don't know why in this iteration it's a little weird. So the problem was was this. So we're gonna shrink this. Okay, and then we don't want negative. So this one definitely do this. And we don't, yeah, we can do this. And then for the smaller sign, I can show you the whole thing. If we have, where is it? We don't like negative on the right hand side. So we need to convert everything to positive on the right hand side. And then if we have smaller sign, we will add a slack variable. If we have larger sign, we will minus a surplus. So that's the idea. So where was I? Here I will have -1 and 2. Here I have slack variables 0 and 0. And this one we can do 1 -5 slack variable, okay. This one, it has to be a surplus 7 -1 0 0, but here -1. And the B vector will be 6 4 and 14. Let's see if that's the same as the MATLAB code. So -1 2 and 1, -1 1 -5 and 1. Okay, the code is so this is right, but it didn't go well. So let's see what happened. We may need to check, stop here, and let's check. Yeah, stop here and then stop here. Let's see what happens. So at the beginning it was okay, and the coefficient tells me the first one should be chosen. Okay. Ratio test. There's so the second one will be chosen. Yes. The next iteration. Here coefficient. The first one is negative. Okay. And then first one, okay. Here ratio test. Last one is chosen, so 3. Okay. This iteration is fine. Here the third iteration, both negative. So chose the most negative one, so then the second one. Yes, second. And continue. So the ratio test, oh, everything explodes.
Yes.
Why is that?
Because only
So the problem was not designed well. What? What happened? A hat, B hat. A hat, J column, ID second. A hat, B hat. What are they?
because the result is all negative.
Really?
Yes, because A all negative and B all positive, so it will be negative.
it is supposed to move along this way. Okay, then I need to figure out why. So if you, in your homework, if you solve up to here, you got full credit. But I need to figure out why we are having this situation right here.
Professor.
Yeah.
Why we don't make x1 bigger than 0 as a function?
X1 bigger than.
Because you say constant x1.
Oh, you mean why don't we choose it as a function?
Yes. Because I think if the crossing point in the below
Because
negative.
by default, linear programming assumes all the variables are positive. So the procedure only allows positive variables. And of course, there are some problems this formulation cannot handle. So now I want to understand why in this particular problem, linear programming cannot handle anymore. So maybe it's, hold on. Maybe I choose the wrong side. Let me see. 0, 0 larger than 40. I think this is the third equation. I chose the wrong side. It should be smaller than the third equation. The third equation was, see the third equation, if I want to allow 0, 0, then if you plug in the third equation, this has to be smaller than. So I chose the wrong side. Because I chose the wrong side in the problem, the correct one should be this. Okay, if I do that, then you are adding a slack variable, not minus a plus. That changed everything. So my mistake was this. Sorry, last time when I was preparing this, I don't know what happened. Maybe I was tired. So that was my bad. Let's change everything to the correct problem by converting this -1 to +1 and solve the whole thing again. You should be able to, I hope you should be able to see the right process. Yep. So for the third equation, if I chose the wrong side, I allow the feasible space on the right hand side, not the left hand side. So in fact, your initial point is not even a feasible point. Of course, that problem is a problem, but it's not a problem that can be solved by linear programming. Linear programming requires all the points to be feasible. I didn't mention that earlier, but it's a fact. If your initial point is not a feasible point, the process will have some problem. Okay? So then you realize it's not powerful enough. Sometimes it just cannot solve the problem. If we are solving a problem on the right hand side, so in that case, the feasible space is right there on the right hand side. Because we want some solution lower than this line and higher than this horizontal line. But on the right hand side of this straight line, then your feasible space is here. In that case, you have to start from a feasible point, not here. Okay? So that's not a problem linear programming can handle well. And also, even if we are doing something like this, we are trying to find the minimum point within this right hand side, there's no solution. because there's no boundary on the right hand side. So when you go right, it goes to infinity. So the solution will be all the way to your right, to the infinity, because that gives you the minimum function value, and there's no constraint on the right. And that's not a solvable problem. If we are solving constraint optimization, we need the feasible space to be properly constrained, well bounded, so we can try to find where the solution is. But if I incorrectly give you the problem like what I did earlier, then that's not solvable. So sorry that you experienced incorrect process. The reason why I didn't program last time, first, it was because I didn't have enough time. Second, I didn't want to give you this code before the homework, because you can just copy the whole thing. It's too easy. And then, but the disadvantage of this is that if I made a mistake, I couldn't visualize it. Yeah, if I have the code last time, I can see, oh, there's a problem. Yeah, I'm sorry. But I'm happy that we figured out where the problem was. So all the problem came from this. So for the homework, if you try this for 1 or 2 iterations and then you see something bad in the third iteration, I'll give you full mark. Okay, this part is my bad. Okay. So that's what I want to cover today. We spent quite some time for linear programming. Any questions? I hope you, with the coding process that you experienced with me today, you understand better how the solution process works. And I'm gonna give you this code later on. In the future, you can use it. But in homework, we realized linear programming cannot solve every problem. So I want to mention something. Let me find it. Okay, so I would like to talk about something that is related to linear programming, and I'm not going to do much in this part, but I think I need to let you know. So in today's further discussion related to linear programming starts with this. So what if we have a problem that is nonlinear? Okay, so we already learned several tricks. First, if you have inequality, you can convert them to equality by select variables and surplus variables. Right? So this is what we we just discussed about. Second thing, if you have nonlinear equations, you can always linearize it. By what? First order Taylor expansion. Okay. But if you have a nonlinear problem and you linearize it by Taylor expansion, that means the original problem is nonlinear. So how do you handle this issue? Because your linearized function is just, they are just approximations of your original problem. So there's an approach called sequential linear programming. So-called the SLP. What does sequential linear programming do? First, they linearize the problem. Then they perform linear programming. And they will check convergence. If not, they will repeat step 1 at the new solution point. If yes, converge. So basically, they will sequentially linearize the problem, perform linear programming, and see if the solution converges. If not, do it again until everything converges. But there is an issue. What if when you are sequentially linearizing the problem and at one of the iterations the solution is not a feasible point? Then it's a big issue. Because from the meta code, you realize linear programming tends to move along the boundary from intersection to intersection until it reaches to the optimal point. So if your starting point is at the middle, or if your starting point is outside of the feasible space, then it's a problem. Okay? So people tries to figure out ways for linear programming process so that the iteration process will be stable. So I'm gonna share with you what I learned from some of the notes, but I didn't program this in the past. So if you are interested in this part and you would like to study further in this part, that could be maybe your project if you want. Okay? I had a student who did sequential quadratic programming in his thesis. He graduated years ago. People usually rely on computer software for this kind of complex process already. Almost no one program by themselves. But the issue is once you rely on commercial software, you have no idea what they did inside the process. So if you are really interested in optimization, you can study further. Okay? So now I'm going to tell you about the issue. Issue when cannot find a feasible starting point. In the linear programming classes. So how do we handle it? So we basically are trying to solve for this is a standard linear programming expression. So what we're doing is, what this trick is about is to introduce a different step, one additional step. That additional step is to determine a possible starting point that is feasible. So this method is called the two-phase method. Okay? So what do they do? What does two-phase method do? Two-phase method will introduce additional variables, even more variables. So let's say you have n equations here, and let's say you have n variables. So your A matrix is in the size of n by m by n, okay? So your x is n by 1, and your b is like this, right? This is m by 1. This is your b. So what two-phase method does is to introduce extra variables. So introduce additional variables. So x n plus 1, 2, x n plus m. And they are going to formulate this equation. So overall, this is m by m. This is many. So there are n of them. Okay? N equals to b. So if you put everything together at the end, you are actually having the original A part and like an identity matrix, right? This is m by n and this is m by m, and you're going to have a very long one multiplying. Here is n by 1, this is m by 1, equals to the same thing. This is m by n. You just introduce a new part here. Okay? And they can be 0, because that does nothing. Right? You can Actually, you don't want them to be 0. You want the original ones to be 0. Then the additional variables can be solved. So this trick is just like what we did for the slack variable when we introduce an identity, but sometimes it's not enough. So you introduce a series of new variables just to find a feasible set of solutions. So in this case, you can start with x1 to xn equals to 0 and solve for xn plus 1 to xn plus m. So in this case, basically you are solving basically xn plus 1 to xn plus n equals to your b, right? So basically, this whole thing equals to 0. So this will be a definitely feasible starting point for this new linear problem. And this part, this so-called two-phase is like in the first original problem, if you have no idea where is a feasible starting point, maybe you can solve for this a different phase of problem. It's not the exact same problem, but that maybe can help you to find a set of solutions that is feasible. But for this extra phase, what is the objective function? So what this extra phase problem can be done is you can say minimize xn plus 1 to xn plus n, subject to what? Subject to this line. Okay, so over here you are not trying to, the optimal solution doesn't mean anything. It's just if you have, for example, if you use, so basically, sorry, this is your starting point of this you can say phase 1 problem, if this is phase 1, okay? So the starting point, if you directly use it for this phase 2, if in this case this will be my phase 2, right? If I call this phase 2. Because the issue is, right now I cannot find the starting point for phase 2. So I have to do phase 1. And when I introduce additional variables, I can easily find feasible starting points for phase 2. And if I solve for this phase, for phase 1, if I solve for phase 1 problems, you should be able to iterate along the boundary. And then we wish at the end all the x become 0. If all the xn plus 1 to xn plus m equals to 0, then you just found a feasible solution that fits ax equals to b. right? So the goal is, if I minimize the sum of xn plus 1 to xn plus m, and you know all the x needs to be positive. So if we are able to find a solution that such that all the xn plus 1 and xn plus m equals to 0, then the rest of the variables will be satisfying ax equals to b. So that solution definitely will be a feasible starting point for this phase 2 problem, the original problem. Okay? So the goal of phase 1 is to find an optimal solution that satisfies xn plus 1 to xn plus m equals to 0. And that x1 to xn would satisfy the following equation, basically a right? And this could be a feasible starting point of phase 2. Basically, the original problem. Right? So I think it's a very interesting procedure. Sometimes in optimization, you don't solve your problem directly. You need to do something further in order to have a good condition for your problem. Then you can start. Okay? So I'm not going to program this part, but I can imagine what kind of issue could happen. Of course, if the original problem does not have a well-defined bounded space, we will have issues. So let's assume we have a well-defined bounded space, but we just cannot find a proper starting point. I think this method should work. I guess one issue would be, what if phase 1 doesn't converge to the solution that you're looking for? What if all the xn plus 1 to xn plus m doesn't go to 0? Then you cannot find the feasible starting point for your original problem. So that would be an issue. I don't have extra notes for that. So maybe if one of you are interested in this problem, you're looking for a topic, you want to work on this, it's possible. You can go search for research papers. There must be, this is not the only way to solve for all kinds of problems in sequential linear programming. Definitely there are so many other approaches. You can go study further from the literature. And if you find something new, I will be happy to listen to your finding. Okay, so this is one thing. The other, next time we will introduce quadratic programming, but I don't have enough time today, so next time. What time is it? before I introduce quadratic programming, there is something very important in constraint optimization. That requires some time for introduction, so I won't go through the whole thing today. I will go through it next time. But there is something called the KKT condition. Conditions, multiple conditions. I will let you know what those are, and later on I will prove why those are so-called the KKT conditions. So if we are solving the problem where we have, we can have we can have a bunch of quality constraints. We can also have a bunch of inequality constraints. Okay? And for the variable, I'm gonna say the jth component of x equals to xj, and j goes from 1 to, let me see, for example, k. Okay, just to define this properly. Okay, so there are three equations to be satisfied. If we can find a solution point that satisfies all three equations, then we are confident it should be the minimum, at least local minimum. So the first equation is partial f partial xj plus summation of lambda I times partial derivative hi with respect to xj. I goes from 1 to n plus summation of mu I this time, but I goes from 1 to n plus gi xj. This equals to 0. So what is lambda and mu? They are so-called the Lagrangian multipliers. Lagrangian multipliers. Okay, this equation sometimes is called the Lagrangian. Actually, no, this is not yet Lagrangian. This is the partial derivative of Lagrangian. So L means Lagrangian. So we will formulate some equation called Lagrangian, and the partial derivative of Lagrangian equals to 0. Defines this equation. Second equation will be mu I g I equals to 0 for I goes from 1 to n. Actually m, because it's is the index for the g. In the third equation, all the mu i's has to be positive or 0 for I goes from 1 to n. So if you have a solution that satisfies all three, then it should be at least local minimum. So a solution point. Including all the x and actually all the lambdas and all the mu's. So lambda and mu now becomes new variables. So when we talk about the solution point, means all the original variables and all the Lagrangian multipliers. If they satisfy the KKT conditions, should be at least local minimum. At least. So in most of our problems, we assume there's a local minimum and it's actually global. So if you can find a solution point that satisfies all these, then it should be at least a local minimum. And if you have a problem that has multiple local minimums, that's not a problem that we are handling at this point. Okay? So we will derive all three equations next time. I will tell you why. If you're curious, you can actually use this to check our solutions from linear programming. The solutions is supposed to satisfy KKT condition as well. So if you are interested, you can do that. Let's try. Let's try to find this particular problem. Actually, let's try the real original problem. Original problem. This one. So this is the real original problem. Before we introduce slack variables, in this case, I need to formulate into a general form for KKT conditions. So this is my f of x1 and x2, that's fine. But in this case, I need to convert my G1 would be negative x1 plus x2 minus 2 smaller than 0. And my G2 would be negative x1 plus 2x2 equals 7 smaller than 0. And this will be my G3 x1 minus 3 smaller than 0. And in fact, we do have these two rules. So that means I have a G4 that is negative x1 smaller than 0 and G5 negative x2 smaller than 0. Okay? So if I need to check all these, I need to formulate into this standard format. And then I will need to figure out what are the I need to formulate so-called the Lagrangian. So in this case, my Lagrangian would be F. I don't have equality, so I only have all the inequality ones. So mu1 G1 plus mu5 G5. Okay? So I have to do the gradient of this. So it's like a gradient of Lagrangian has to be 0. That's my first equation. So actually, it's let me show you. This is negative x1 minus 2x2, right? So if I do basically the gradient would be partial Lagrangian over x1, partial Lagrangian over x2, partial Lagrangian over mu1, da da da. It's actually a long process. Mu5. Okay? So if you try it, at the end you will see the first term would be negative 1 minus 2 mu1 minus mu2 plus mu3 minus mu4 minus mu5. That's, oh no, there's no 5. That's the partial derivative with respect to x1. The second term will be negative 2, and then plus mu1 plus 2 mu2, 0 here, 0 there, and then minus mu5, right? And then partial derivative with respect to mu1, what you get at the end is actually g1, and then g5. Okay, and this equals to 0. So not the sum of it, because when I do, oh no, I'm right. Yes. This has to be 0. Every one of them equals to 0. Is that right? Sorry. No need the following. We don't need these. So just these two. Just these two. Only partial derivative with respect to x. So only these two. Yeah. Because this part didn't mention partial derivative with respect to Lagrangian multiple. You don't need to. Okay, so only these two. Then I need mu I gi equals to 0. So mu1 times, well, I can copy this one. Copy. Paste. mu2, mu3, mu4, 5 equals to 0. And all the mu's has to be positive or 0. So if I can find a solution that satisfies this, then that's the solution. So what was the solution? Let's go back to MATLAB. If I solve for this problem, the solution was 3 and 5. So if from linear programming, I realize the solution is 3 and 5, right? I just want to check whether 3 and 5 satisfy all these. If it does, KKD condition says, okay, this is solution. So just plug in. From here, I can already tell mu, these two are 0, definitely, because 3 and 5, right? So 3 plug in here. Okay, so this part is 0. So these two already satisfy. This one satisfy because 3 plug, x1 equals 3 plug in. Now I just need to check the first two equations. And mu minus 2 times 3 plus 5 minus 2. This is 1. Mu 2 b plus 2 times 5 minus 7. What are they? So it's a negative 3 times mu 1. Okay, this has to be 0. So mu 1 is 0. This gives me 0 times mu 2. This has to be 0. So mu 2 can be any value. So just pick up some number that is positive or 0, either way. So this one satisfies, this one satisfies. Mu 2 can be any positive or 0 value. Mu 3 same. Mu 3 can be any positive or 0. So when I plug in this optimal solution, the first two equations satisfy mu 1, 0, mu 2, any positive value, mu 3, any positive, mu 4, 0, mu 5, 0, okay, all satisfied. So it seems like it's a solution. Does it mean if I plug in something else, it will satisfy? Let's try something else. So if I try x equals to something easy, just 1, 1, okay? And then I try to plug in the whole thing again. In that case, I will have mu 3, 1 minus 2 must be 0. So in this case, mu 3 is 0. Mu 4, negative 1 has to be 0, so mu 4 is 0. Mu 5, negative 1 has to be 0, so mu 5 is 0. So the bottom three equations satisfy. Then only the first two, mu 1, mu 2. I'm using 1 and 1, so negative 2 plus 1 minus 2. This has to be 0. This one, negative 1 plus 2 minus 7. This has to be 0. So in this case, mu 1 has to be 0. Oh, also satisfied. What? Did I miss anything? Oh, I forgot to check these two. I need to check the whole thing again. I missed there are two equations on the top. So, sorry, let me check the first situation. I haven't checked the top yet. So here, negative 1 minus mu 1 is 0. Mu 2 we don't know yet. Mu 3 we don't know yet. Mu 4 0 has to be 0. The other equation minus 2 mu 1 0, mu 2 don't know yet, mu 5 0, right? So from here mu 2 equals to 0, mu 3 equals to 1. So satisfy what we are looking for, either positive or 0. But over here, now I need to check these two. I haven't checked this yet. So in this case, the whole thing equals to -1. This is -2. So not 0. So not optimal. See? So I tried a different point. From the bottom, from here, I realize mu has to be all 0. But if I plug in here, I realize, okay, these two equations are not 0. So at the end, it tells me this point is not optimal. Okay. So, it seems like it's working. But next time I will derive some equations and let you know why those are making sense. So that will be the first part of next lecture. And some of the equations are important for quadratic programming. So I will introduce KKT condition first, prove it, and then talk about quadratic programming. And for the quadratic programming, I may not be able to do some coding. I'm not sure, it really depends on the time. Okay, so that's it for today. Any questions? Okay. Oh, I should give you homework. Can I skip one? Are you guys okay? Or do you enjoy optimization so much you just need homework? I guess not. Okay, let's skip one. So no number 5 here. That means I will be doing this. Do I do so? There's no score. Oh, I'm really ahead of the progress. KKT was supposed to be after the midterm. Let me get rid of all these for now, and then we will determine whether we will do homework. Just get rid of those. So now I don't have enough points yet. I need to give you more homework in the future. I have, there's a 2 point. Because 4 homeworks. So far, 4 homeworks. So totally, yeah. On the course, you have 90 at most. Okay. I guess I should do attendance. Otherwise, there's no attendance score. So let's do attendance now. Okay, 刘嘉伦 ，okay, 杨俊强，哲轩 ，okay, 凯云 okay, not here, no. Harry, okay, this, okay. Lini Yang, CEO. Fong, Mary, okay, Matthias, no, okay. After Stevie Jason, someone just give up. Zhong Wei, okay. Yi Jun, okay. Bing Chen, Yao Zhong, Li Ci, Wei Yan, Zhen Huang, okay. 韦志宇 ，Emma， 对，Dewanda， 凯琪，玉君，燕如 ，Young Ro， okay, good. So I guess they will give up. I hope they don't drop it. So I fail them. I don't need to fail you. That's always my trick. So I don't let everyone pass. So please pray they don't drop. So I can fail them. Okay, that's it for today. See you next time. Oh, by the way, Saturday Example. Conjugate gradient and linear progression.